For today's curve sketching video, we're going to cover a rational function and a rational function with a radical. This curve sketching video does not cover derivatives, but our next one will. First, we're going to identify the domain. The domain is anything except for zeros of the denominator, right? We cannot divide by 0, so anything that makes this denominator equal to 0 will be a restriction from the domain. So 0 is a restriction, 1 is a restriction, and 3 is a restriction. So to write my domain in interval notation, I will go from -infinity to 0, union 0 to 1, union 1 to 3, union 3 to infinity. Next, we're going to show its reduced form. So g of x, we have 1x that reduces, one of the x minus 1 factors reduces, and nothing else. So I'm going to have x minus 1 to the 1, x plus 3 to the 3, over x times x minus 3 squared. Now our vertical asymptotes will be the zeros of the reduced denominator. So if it will make the reduced denominator equal to 0, then it's a vertical asymptote. That means that 0 is a vertical asymptote and 3 is a vertical asymptote. This factor, x, is to the power of 1, making it an odd vertical asymptote. This means the behavior on either side will be different. And x minus 3, this factor, is to the power of 2, making 3 an even vertical asymptote, which means the behavior on either side will be the same. Wholes come from the factors that reduce. So we had two things reduce. We had an x over x squared, so x equals 0 could tentatively be a whole, but it's a vertical asymptote. So if it's a vertical asymptote, then it's definitely not a whole. The other thing that reduced was x minus 1, so the 0 of that factor would be 1, and that's going to be the x value of our whole. How do we find the y value? We're going to plug it in to the reduced form. I'll write RED for reduced form. If you plug it into the original, then you'll get undefined, and that's equal to 0. To find the x-intercepts, we're going to make the function equal to 0. I'm going to use the reduced form because it's much simpler. And in order for this function to equal 0, that means the numerator is equal to 0, as long as that doesn't also make the denominator equal to 0. And here we would have x equals 1 and x equals -3. Those would be my x-intercepts. But I have a problem. X equals 1 is already a whole. Can it be a whole and an intercept? No. If it's a whole, then it's undefined. Therefore, it cannot be an intercept because an intercept is defined. So x equals 1 is not going to be one of our x-intercepts. -3 is our only x-intercept. To get our y-intercept, we plug in 0 for x. Oh, wait. 0x equals 0 is a vertical asymptote, so we do not have any y-intercept. And to determine our end behavior or end behavior asymptote, we're going to need to look at the term of highest degree in the numerator and the term of highest degree in the denominator. In the numerator, we have x to the 1, x to the 2, and x to the 3. So that will end up being x to the 6. And then in the denominator, x to the 2, x to the 1, x to the 2. That's x to the 5. Our numerator has a greater exponent than our denominator, which means we're going to have a slant asymptote. A slant asymptote means we use long division to determine what that asymptote is. So I'm going to do the long division on the reduced form, but I will need to expand it. All right, after expanding, let's divide. X to the 4th divided by x cubed is x. Oh, look, we don't even have an x term in here. I'm going to add one of those. Multiply -6x cubed and 9x squared. Go ahead and subtract. 8 plus 6 is 14x cubed plus 9x squared. All right, 14x cubed divided by x cubed is 14. Multiply. An x cubed term won't go into, so whatever we're left with is the remainder. And you know what? We don't have to write the remainder because we have our slant asymptote at y equals x plus 14. I believe it's time to sketch the graph, so I'm going to start off with my vertical asymptotes at 0 and 3. Now, the intercept that we got was from this factor, x plus 3, and that is to the power of an odd number. So guess what? This is an odd x-intercept. What does that mean? That means the graph will cross the x-axis. It will not just touch, it will actually cross at -3, 0. It's not important to know if our hole is odd or even unless it is a hole at the x-axis. Wow, so this one is a candidate for us to determine if it is an odd hole at the x-axis or an even hole at the x-axis. So what we reduced was an x minus 1 over x minus 1. That was to the power of 1, meaning this is an odd hole. The graph will cross through the hole, of course not defined at 1, 0. It will not just touch the hole, it will cross through it. So my x-intercept is at -3, and my hole is at 1, 0. And our slant asymptote is at y equals x plus 14. But remember that horizontal or slant asymptotes only determine end behavior. They do not determine behavior close to the vertical asymptotes. So this slant asymptote looks like it's about here and here. Based on the holes, the intercepts, and the vertical asymptotes, if you can tell if they're even or odd, and remember you can only tell if the hole's at the x-axis, but if you can tell if they're even or odd, it gives you so much behavior around those points so that you really don't have to plug in that many points, if very many at all. So I'm going to plug in -1 into the reduced form. G of -1 is 1. We are going up from here. And we know that we cross the x-axis and we hug the slant asymptote. All right, because this is an odd vertical asymptote, we know the behavior on this side will go to -infinity. Because this hole at the x-axis is an odd one, we know we're going to cross through it. And because this vertical asymptote is even, we know the behavior up here will be the same, which means we will hug the slant asymptote above. So let's write our vertical asymptote limit behavior. The limit as x approaches 0 from the left of g of x is positive infinity. The limit as x approaches 0 from the right of g of x is negative infinity. The limit as x approaches 3 from the left is infinity, and the limit as x approaches 3 from the right is also infinity. Our end behavior is written f of x approaches something as x approaches infinite positive numbers, and f of x approaches something as x approaches infinitely negative numbers. As we're approaching positive, we're headed toward, this is a g of x graph, we're headed toward positive infinity. And in this direction, we are headed toward negative infinity. Example 2. The domain restrictions are anything that would make the denominator equal to 0, or anything that would be negative under a root. But this one's just root x squared, so we know nothing will be negative underneath that root. So it looks like the only restriction here is at x equals 0, because square root of 0 is 0 and we can't divide by 0. That gives us negative infinity to 0, union 0 to infinity as our domain. Now nothing reduces from here, so we're not going to have any holes. Intercepts. All right, so x-intercepts are found when we make the function equal to 0, and that would be -1. Would make the numerator equal to 0. So my x-intercept is at -1. To find the y-intercept, we make x equal to 0, but if we did that, we would have an undefined expression, so there are no y-intercepts. Speaking of 0, that is a vertical asymptote. Restrictions of the denominator. After everything's been reduced, if you can reduce, those are vertical asymptotes. To determine our end behavior, we're really asking ourselves, what is the limit of the function as we go toward positive infinity, and then what is the limit as we head toward negative infinity? So let's evaluate those limits. If we're evaluating a limit toward infinity, then we really only care about the terms of highest degree, like the x in the top, and then we can rewrite this square root of x squared as absolute value x over absolute value x, or absolute value x over x, gives me two options. It's a piecewise function. If my x's are less than 0, then I'm going to have a -1. And if my x's are greater than 0, then my result is +1. So if I were to evaluate these limits, for the first one, we're headed toward negative infinity, so this is equal to -1. And for the second one, we're headed toward positive infinity, where x is greater than 0. So this one is headed toward +1. F of x approaches -1 as the x's approach negative infinity. And f of x approaches +1 as x approaches positive infinity. Now, our vertical asymptote, is that even or odd? The factor that gave us x equals 0 as a vertical asymptote is x to the power of 2. So, our vertical asymptote is even. Let's graph our vertical asymptote, our intercept, and our horizontal asymptotes. And I know this is an even vertical asymptote, which means the behavior on either side will be the same. Our intercept, was it even or odd? Are we going to cross that x-axis? Are we just going to touch it? Well, the factor that gave us our x-intercept was x plus 1, and that was odd. So this is an odd intercept. We'll be crossing the x-axis. So let's plug in maybe 1, just to see what's going on this side, and then I think I'll be able to figure the rest out. When you plug in 1, you get 2. All right, that means this one's going to be above, this one's going to be headed toward positive infinity, and we'll be hugging the top of this horizontal asymptote. All right, this is an even vertical asymptote, so I know this side is also headed toward positive infinity, which means this will just come down to hug this horizontal asymptote. And then we'll write our limit behavior. As we approach 0 from the left, we get, honestly, as we approach 0 from either side, we get positive infinity because we have an even asymptote. We could have written that on example 1 as well.